It is once again my pleasure to welcome all of you to this Royal Statistical Society Applied Probability Section meeting. I'm very happy to have you here. It is now time to welcome our first speaker, who is Johan Heine. And he will be talking about recent advances in large sample correlation matrices and their applications.
Thank you very much for the introduction and for the invitation to speak in this section meeting. I will be talking about some topics that kept me busy for the last around 1.5 years. This is joint work with Jeff Yao from Hong Kong University, Sam Johnston, who is now in Bath, Joshua Pochner from Graz, my colleagues Anna Gusakova and Christoph Taylor from the University Bochum, and Nestor Parolia from TU Delft. If there are any questions at any point, feel free to interrupt me. The title of the talk is Recent Advances in Large Sample Correlation Matrices and Their Applications. Okay, so we have these IID vectors x1 to xp in Rn, and we arrange them as the rows of this data matrix. From those, we construct this simplex, where the vertices are zero vectors and those x1 to xp. This is a convex body in n-dimensional Euclidean space, but it is at most p-dimensional, so it makes sense to study the p-volume of this simplex. And for this, we have the following representation, namely it can be written as 1 over p factorial times the square root of the determinant of x times x transpose. So since this is a random matrix talk, we will be thinking about this p-volume in terms of this determinant on the right-hand side. And the goal will be to derive fluctuations for this log volume of the simplex. And in the high-dimensional regime, where p will always depend on n and tend to infinity as n goes to infinity, and p is at most n. Otherwise, this volume is automatically zero. Okay, so if I go back to this identity that I had, if I take logarithms on both sides, then I obtain this equality here. So in order to study this log volume, I just need to study the log determinant of this sample covariance matrix x transpose. And what I will do in the first part of this talk is to provide an overview of various models for x and present some CLTs for this log volume. By the way, you can hear me, right? Because I can see nobody here. Okay. So let me just recall, we have this identity for the log volume, and I will classify the structures for x as follows. I will consider 3 groups. So a basic class where there exists an explicit stochastic representation in terms of sums of well-known random variables, for example, normal random variables or gamma random variables or beta random variables, so where you have no density, where you know moments and whatever you like. And then I will say that we have a basic representation. The second class, the intermediate class, where there exists no basic representation, but you have a certain structure in this matrix X. And here, by the structure, I mean either independence of the rows or the columns of my data matrix. And in the third group, you have the advanced class. There's no basic representation, and even possible nonlinear dependence between all the entries of the data matrix. I would really appreciate some feedback if you can still hear me, because I cannot see a chat or I cannot see myself. So
yeah, I can hear you and everything is fine.
Okay,
Carry on.
okay, that's nice because
all is good.
I've used this tool in a year. Okay, so let me start with the first group, those basic representations. And I will start with some examples from Julian Grote, Zahara Plutschko, and Christoph Thiele, and also Peter Eiselsbach and Hannah Döring have worked on these. The first model is the Gaussian model, where the vectors, where the coordinates of those vectors xi are just standard normal random variables. The second one is a beta model with parameter nu, and here just I wrote down the density for this beta model, which is quite common in stochastic geometry. I just put the formulas for this density here to not get confused with the usual beta distribution that I will need later on. Then I will consider this beta prime model with some parameter, which is given by this, which has this density. So in both these cases, the vectors xi follow this distribution. And then the fourth one, the spherical model, where the xi's are uniformly distributed on the unit sphere. And the reason why I highlighted this one in red is that essentially all these four models are the same. And I will just give the argument for the spherical model, and then we will see how they are related when we are studying this p-volume. Okay, so for the spherical model, let me write down the stochastic representation that we have. And this is the following, so that we have just a sum of log beta random variables. So these beta ij here are just independent beta variables, so beta ij random variables. So this is a sum of independent random variables. And now, if we would like to derive, let's say, a central limit theorem, this can be readily done via standard methods. For example, using a the Lindeberg CLT, and just check the conditions. Then if you center by the mean and divide by the variance, you obtain a standard normal distribution in the limit. And now let me explain what these four models that I introduced, namely this Gaussian, beta, beta prime, and spherical model, have in common. Namely, they are all rotationally invariant. And I recall that a vector xi is rotationally invariant if it can be written as the following product. So some radius ri, which is independent from the direction ui, and ui is uniformly distributed on the unit sphere, so n-dimensional unit sphere. And so this means that these four models just have a different radius. And for the spherical model, for instance, the radius would just be 1. And now let's try to use this representation here. And let me introduce a diagonal matrix where I collect all the radii on the diagonal. And then a matrix Y, which contains the directions. So the rows of this matrix are just the UIs that I had before. And then I can rewrite the determinant of XX transpose as the determinant of this matrix here, just plugging in because X equals D times Y. And I can rewrite it like this. And this determinant is just the product of the diagonal entries here. So then if I take the logarithm, this identity, I end up with a sum of two terms. One is the sum of the log radii, and the other one is the log determinant of this y transpose. And this this matrix Y just consists of these random directions, so on the unit sphere. So this boils down to our spherical model. And for the spherical case, we have seen a representation in terms of these log beta random variables before. So then it follows that this log volume can be represented as a sum of these, so up to this constant here, sum of these two terms here. And this one we have basically analyzed before, and this one is even simpler. It's just an IID sum. And the important thing to note is that all the terms on the right-hand side are independent. Okay, and now we can try to study those two sums, Sn1 and Sn2 separately. And so let's start with Sn2. If you center by the mean and divide by the variance or some sequence which is asymptotically equivalent to the variance, it can be shown that you converge to a standard normal distribution. And in the weak sense, and for this first sum, Sn1, you can look for conditions that to convergence to a stable random variable. For example, consult the book of Petrov, and you will find various formulas how to choose this Bn and this sigma n, and then you can obtain, depending on the distribution of this Ri, which is completely unspecified yet, you can, for instance, obtain an alpha stable distribution where with alpha less than 2 you have an infinite variance distribution in the limit, and for alpha equals 2 it's just a normal distribution again. And now what you have to do is just compare those sequences omega n and sigma n, and depending on which it is, so if omega n is much larger, then of course the contribution from this Sn2 will dominate in the limit, otherwise the one from the Sn1, and if they are of the same order, you can get a combination of this normal distribution and these alpha stable laws in the limit. Okay, and this is what I wanted to say about these rotationally invariant rows. Now let me move on to the intermediate case. I will make a slight extension of the previous case. Instead of rotational invariants, I assume that the xi are elliptically distributed. The only thing that's different from before is that I add some deterministic matrix A here. The radius and the direction are still the same as before. This makes the whole business somewhat more complicated, but we can start in the same way as before by collecting the radii in this diagonal and introducing this matrix Y, where you still have this, where now additionally there is this A. And as in the spherical case, we get this nice representation. The radius again can be separated from the direction, and now you have to solve for the log determinant of this matrix Y times Y transpose. And this can be handled as well using some base times height formula, essentially to compute the volume of the parallelotope, and then some Taylor expansions combined with some martingale techniques. You can show a CLT for this log determinant. And this is technically more involved, and I will not go into detail here. Instead, I want to ask another quite natural question that what happens if you have different entries? For example, consider heavy-tailed entries. Heavy-tailed entries in the sense that certain moments don't exist, or that you have just power law tails. Just think of a Pareto distribution with so a tail of the kind x to the minus alpha. The sample correlation matrix, which is defined here, sample correlation matrix R. So it is just a sample covariance matrix x transpose. Then you multiply from the left and the right with the diagonal of x transpose to the minus 1/2, where this diagonal is just stands for a diagonal matrix with the same diagonal as this as x transpose. And okay, I assume that these entries are already centered because otherwise I would have to center by the sample mean, and the formulas get a bit more complicated. And for presentation, this is an easier form.
I think the in the screen isn't sharing anymore for me. I don't know if anybody else is seeing.
For me, it's sharing, but maybe you can reshare it.
That's okay. I'll try to relog on. Sorry about that.
Okay.
Okay. Let me know if I shall stop and share again if this is an issue for more people. Okay, so recall that before we had structure just x transpose, so some matrix times its transpose, and we can write this R again as some matrix times its transpose. If you define this first part here, this first as our y, then we can clearly write it as y times y transpose. And this y now has independent rows again, since you basically divide each row of this matrix X by its Euclidean norm. Okay, so that's why we are in this intermediate case. And here is the result for the log determinant of this sample correlation matrix, the first one that I want to present today. And this is in the kind of the most standard setting in random matrix theory, where we assume that the dimension P and the sample size N tend to infinity at the same speed, and the ratio approaches some constant gamma in 0, 1. And I assume that the entry distribution of X is regularly varying with an index alpha between 3 and 4. So just think of tails of the kind x to the minus alpha times some slowly varying function, which you may as well interpret as a constant. Then as n to infinity, you have the following CLT, where now the centering and the scaling is explicit. And I would just want to briefly point out this result is already known for a finite fourth moment, which is often a crucial condition in random matrix theory. And here, to the best of my knowledge, this is one of the first special types of result in the direction of linear spectral statistics for sample correlation matrices under an infinite fourth moment. And I will show you some simulation of this later on. Okay, so this was the correlation matrix with a kind of identity population correlation matrix. Now I want to study a non-trivial correlation structure, which will be given by this matrix sigma here. So I will again start with some noise matrix X, which has IID centered entries, and then define my data matrix a little bit differently. I will multiply this noise matrix with the Hermitian square root of sigma, and the sample covariance matrix is non-normalized, so is given by this data matrix times its transpose. And the sample correlation matrix I define as before. Now I just write down the entry-wise definition. It's the empirical covariance of the ith and the jth coordinate divided by the corresponding empirical standard deviations. And as we have, let me just briefly mention some applications of this logarithmic determinant of the sample correlation matrix. First of all, the sample correlation matrix is often used for data analysis, and a popular object in multivariate analysis. You can refer to some textbooks that are standard textbooks that I've listed here. In particular, the log determinant of the sample correlation matrix is the likelihood ratio test statistic for independence or uncorrelatedness testing. And as we have seen in the beginning of the talk, in geometry, the determinant of R describes the volume of a simplex or of some parallelotopes. Okay, so now let me return to this sample covariance matrix here with this population covariance sigma, and let the spectral norm, so the largest eigenvalue of sigma, be uniformly bounded. And then the population correlation matrix, here denoted by gamma, which is the true correlation matrix underlying the model here, is given by this expression. So it's the same definition as R, just replace S by its expectation. And we are now interested in a central limit theorem for this log determinant. And in the literature, this is available in two cases. First of all, in the case of normal distribution, so where all the entries are normally distributed, and the case that the population correlation matrix gamma is the identity. So in other words, if the sigma is not here. And this has been studied in these three papers here. Note that Jiang is a huge fan of sample correlation matrix, and especially in high dimension. And he has not only studied the log determinant of sample correlation matrix, but also hugely contributed to the development of the theory on the largest entry of sample correlation matrices, which is the backbone for these threshold estimators in high dimensional statistics. So apart from this normal distribution or gamma as identity, nothing was known. So let me present the new result that we found. And for this, we will assume that our noise random variables, okay, they are independent, mean 0, variance 1, and a finite fourth moment. And if the spectral norm of gamma is uniformly bounded, and in this high dimensional regime with P over N converges to gamma in 0, 1, where P is at most N, this is not a real restriction, because if P is larger than N, then the determinant is just 0. you can write down those mu n's and sigma n's that you need to obtain a central limit theorem. And we found these explicit formulas. Note that it also includes the case that gamma equals 1, which and thereby unifying some results in the literature that where even for some covariance matrices, those cases are typically separated. And I want to point out one fact about this in this formula, namely the term here in red. On the previous slide, I told you that in the case of normal distribution and that gamma is identity, these were known. And so in case of normal distribution, this fourth moment is just 3. So this red term disappears. And in the other case, where gamma is the identity, then this constant C gamma here, which is defined here, is 1. So then also this factor disappears. This is the extra term that you get when you have non-normality and non-IID case. And okay, let me maybe show you some simulations that this actually works quite nicely. So what we did here is we simulated this log determinant where the entries follow a t-distribution with alpha degrees of freedom in dimension 300, and the n is 1000. And so for one such simulation, you compute the log determinant, and then you repeat this 400 times. And this is the histogram of the values that we obtained. And the blue line here is just density of the standard normal distribution. And you see this is looks like a very good fit. And then we vary the parameter alpha here. And of course, as long as alpha is larger than 4, the fourth moment is finite. So all the assumptions are satisfied. So this is the case alpha equals 5. But interestingly, this also works if alpha is below 4, and which hints at a very robust test statistic. And so this is with alpha 3.5, and this is justified by the result that I showed you before with this regular variation. And this is so far just available in the IID case. But this threshold alpha equals 3. So I should maybe mention that the lower the value of alpha, the heavier the tails are of the entries. So, and then if alpha is too small, this breaks down. And the alpha equals 3 seems to be the threshold. And it will be interesting to find out exactly why alpha equals 3 is so important. Okay, so this was the first part of the talk. If there are some questions about this part, then I would invite you to ask right now.
I have a question. Can you provide any intuition about why this result still holds for gamma equal to 1? So one would think that, well, if we are talking about just covariance matrix, not correlation, then just one of the eigenvalues very close to 0, right? And
yes.
Log determinant should something weird should happen to that. But you have a nice result for gamma equal to 1 as well. So could you just give some intuition?
Okay, this is an excellent question that you ask. And indeed, there's a different phenomenon happening in the case gamma equals 1. So if gamma is 1, if you look at the variance here, this variance tends to infinity. And if gamma is below 1, then this variance tends to a constant. And so for instance, if p equals n, then the variance is of order log n, and you need slightly different, or actually very different arguments in the proof to combine these two cases. And it gave us a lot of headaches to come up with this unified formula. Also, it's very delicate, this p minus 1 here. And if you maybe know the paper by Pan and Wang in Piet and Bernoulli, where they did this kind of something similar, for example, covariance matrices, they had similar formula, but if you put here p, for example, you would have to remove this 1. And yes, but the short answer to your question is as long as that even in these cases, the R is not singular, and that's what's important.
Can I just clarify? You are saying that P over N converges to gamma, which is constant, but from formulas, it looks like the result still will hold if gamma is changing. So suppose that gamma is approaching to 1 at some rate. Is it still, your result still true?
This holds for any gamma in 0, 1.
Okay. All right, sorry. Yeah, I see.
Okay. And
so if I may, another question. So do you have any idea as to where this cutoff of alpha equals 3 comes from? Because usually the regimes are, bigger than 4 moments, 2 to 4 moments, and less than 2, and maybe less than 1. But usually the regime where your tail has a variance but not a fourth moment, well, it's usually unified in some way. But here you seem to have another cut in between, right? So something happens at 3. Do you know what it is?
We saw here before.
Yeah.
This comes from when you compute this variance. Actually, there are some error terms, and they don't vanish if alpha is too small. And we checked in simulations that actually really something different happens in these cases. And we don't know yet what is the different thing. Maybe you need some extra term in the centering and the scaling. But at least this formula that would also be valid for covariances, for example, doesn't hold anymore.
Okay, so there seems to be a raised hand.
Yes, so that's me. I just wondered, as we are asking questions already, can you say anything about the rate of convergence for these center limit theorems?
No, we didn't look at the rate of convergence.
Okay, thanks.
But for the first part, for the models in the first part where you have this in the rows, it's a bit simpler, and we uploaded a paper recently. So this is this paper here with Sam Johnson and Joscha Prochnow, thin shell properties, and there we focused on various sane rates. But this does not apply to the statistical setting because it's a bit different with the rows and columns. Okay, yes. But let me maybe go on because I have still want to go to this other interesting topic that I find very fascinating. Namely, okay, so for this now I start again with my data matrix, which is P times N, with IID symmetrically distributed entries in the domain of attraction of a stable law with index alpha in 0, 2. So again, infinite variance. And whenever I say something about this entry distribution, I will do this in terms of this generic random variable X here. Then the sample correlation matrix is defined as before. And I will need the ordered eigenvalues of R noted by lambda 1 of R, the largest eigenvalue, up to lambda p, the smallest eigenvalue of the sample correlation matrix. As most of you know, this empirical spectral distribution is a very useful tool to study these eigenvalues. And in random matrix theory, one often looks at the limit of such empirical spectral distributions, where you want to look for weak convergence of such a sequence of spectral distributions. So first question, what is the limiting spectral distribution of the sample correlation matrix? In the case alpha equals 2, it is the Marchenko-Pastur law with parameter gamma. It is fully described by this density. There are also formula for its moment. This distribution is compactly supported on this interval from A to B, and everything here is very nice and fully explicit. And the same holds for simple covariance matrices, as long as you have a finite variance. In the infinite variance case, which can be obtained by choosing this parameter alpha smaller than 2, Benarous, Guinet, and Belinci, and others have studied the limiting spectral distribution of this sample covariance matrix under infinite variance. And they assume that the entry distribution is in the stable domain of attraction with some alpha smaller than 2. And then you can show, for example, the following result. If you normalize these matrices correctly, namely by certain quantile of the entry distribution, then you converge to some distribution G alpha gamma, which has a density, and the density has this behavior at infinity. So the support is infinite. And however, there's no exact formula, and I'm sure there are some open questions. And I think also that the third speaker of today, Sandrine Péché, has worked in this area, and it would be interesting to get her opinion as well. What could be the open questions in this area? The question that I was interested in was the infinite variance regime for sample correlation matrices. This is the sample covariance side. And for sample correlations, there is also a limiting distribution, which we characterized by its moments. And this law has some connection to this Marchenko-Pastur law, and also depends on this parameter alpha. So the name we came up for it was alpha heavy Marchenko-Pastur law. And this alpha heavy Marchenko-Pastur law is uniquely characterized by its moment sequence, this mu k, so the kth moments, and it depends on alpha and the parameter gamma. And this kth moment can be written in the following way. So the first 3 moments coincide with the moments of the Marchenko-Pastur law. So beta k is the kth moment of the Marchenko-Pastur law. And from 4th moment and higher, you get some positive term dk of alpha gamma on top to these Marchenko-Pastur moments. Okay, so this is the simplified formula for these moments. I want to apologize beforehand for my next slide, but I thought for the sake of completeness, I will show you the expression also for this decay of alpha gamma. So this is on this slide here. You see the first contribution, this Marchenko-Pastur moment, is very nice, and it's given here at the bottom. And then the rest is, so this decay of alpha gamma, a couple of sums, some gamma functions, and need to do some counting of graphs and weigh them accordingly. The formula looks rather involved. However, we've presented some nice algorithms to compute them, and the first 6 or 7 you can are doable by hand, but then it doesn't look so pleasant. Okay, but anyway, so this characterizes this alpha heavy Marchenko-Pastur laws. And instead of showing you the formula, I will show you some pictures to kind of give you a rough impression of the shape and what actually changes relative to Marchenko-Pastur. So this is now in dimension 1000 and n 5000. And the noise is simulated from a t-distribution with alpha degrees of freedom. And so I plot the histogram of the eigenvalues of the sample correlation matrix. And then I compare with the blue line here, which is the Marchenko-Pastur density with parameter p over n. The blue line, blue function here is the same in all 4 plots that you see. And what varies here is the parameter alpha, which controls the tail heaviness. And you see that for alpha somewhat close to 2, it looks roughly like Marchenko-Pastur. However, you have some eigenvalues outside the support of the Marchenko-Pastur law. Okay, by the way, I should also mention why I'm comparing with this Marchenko-Pastur, even though it's not the correct limiting spectral distribution. The reason is, of course, that we were not able to extract some density from this formula. Okay, and then if you make the tails heavier, so for alpha equals 1, you have still mass outside the Marchenko-Pastur support and more concentration around 1. If you increase the heaviness of the tails, this phenomenon becomes more pronounced, so more mass around 1, and eigenvalues way outside the support. And for the very heavy tail case, so let's just say alpha is 1 over 10, it almost looks like a discrete distribution. And I will show you an explanation for this last plot at the very end. What you can also look at is the empirical moments. That's also how we started our proofs, by looking at these empirical moments and studying their limits. So here, if you take the eigenvalues raised to the kth power and sum them all up, so this is what is plotted here for k equals 2, 3, 4, and 5 in these columns. In the top row, you see the simulation from a t-distribution with 1 degree of freedom. And the mu's are those moments of this alpha heavy Marchenko-Pastur law. And for sake of comparison, I did the same simulation where this is each from 1000 runs, from again with dimension 1000. So the bottom row is from a normal distribution, where you even have a CLT for these empirical moments. And note that the mu2 and the beta 2 coincide, the same for the 3, and then for the 4th moment onwards, the mu4 is always larger. But the most striking fact is the difference of scale on the x-axis. So, for example, if we just look in the in the standard normal case here, it goes from 3.85 to 3.9 on the x-axis. And here for the t distribution, the heavy tail case, it is from 3 to 6. So it's a much wider range here. Okay, this is also something that could be very interesting to study and establish these fluctuations. Finally, we tried to extract as much as possible from this complicated formula, and in particular, we took the limits for alpha tending to 0 and alpha tending to 2. So clearly for alpha equals 2, there is the Marchenko-Pastur law, and indeed also these moment formulas are continuous in alpha in this sense. So for alpha to 2, you obtain the Marchenko-Pastur law. And for alpha to 0, you obtain a modified Poisson gamma distribution, which is defined by these point probabilities. In particular, if you set gamma equals to 1, then this is just the Poisson distribution with parameter 1. So the e to the minus gamma point mass is at 1 and at 0. And if you simulate this, okay, somehow you cannot simulate alpha equals 0, so I simulated alpha equals 0.05. And what you see there is in the height of these bars, so for the Poisson distribution with parameter 1, the point masses at 0 and 1 are the same. And this is nicely reflected by the height of these two bars. And then there are some exponential decay. While if the parameter gamma, which is the ratio p over n, is smaller than 1, then the point mass at 1 is always the highest, and then you have these exponential decays. And yeah, from these pictures, I think you can see this almost discrete behavior in a very nice way. And I have to say, I was very surprised when I saw this for the first time. So I think I'm out of time. So let me thank you for your attention.
All right, thank you very much. I guess I'll be the only one clapping since everyone is muted. I'm sure they're all clapping very, very strongly. So are there any questions?
I have
Any
a
other
question.
questions?
I have a question. Can I ask?
Yes.
Well, do you have any empirical results on the speed of convergence of the, I don't know, cumulative distribution function, for example, to this kind of generalized Marchenko-Pastur thing? So from your histograms for empirical moments, it looks like the speed of convergence should be slower, much slower, right? Or I'll just if you compute, say, Kolmogorov distance between empirical distribution and the limit. So how do you have an idea of
between the empirical distribution and
the limit? The limit. So will convergence be very slow to 0? Like just do you have any idea about that?
Well, that's definitely a good question. I mean, this work that I presented is the first one, as far as I know, in this direction, and it was more about identifying, characterizing this limit. The problem is that this formula is still leaves something to be desired. For example, so how can I do this comparison that you suggest if I just have this formula for the moments? And this is, I think, at the moment not feasible yet. But And also questions, for example, what is the support of this new class of distributions would be very interesting to find out.
So, yeah, I mean, like you could have, I'm not asking about theoretical result, but you could have, for example, produced histograms for the quantiles of empirical distribution of eigenvalues and see that they are very volatile, let's say, or something like that. And that would give some idea about the speed of convergence.
Yes. Yeah. Mm-hmm. Yeah. Okay. Something in this direction, maybe. What you can see from these plots here, that there's a lot more variance involved than in these light-tailed cases when you have a finite forward moment. And so yes, there is. This can be analyzed, but at the moment I would have to look much more into this to be able to give you any reasonable guess.
All right. Is there anything else? Any other questions? All right. Well, in that case, thanks, Johan, again. And we will proceed to our next talk. We're back at our meeting. It is my pleasure to welcome Sandrine Pechet, who will talk about some non-linear random matrix models.
Okay, so thanks for sharing my file. Thanks for the invitation. And this is joint work with Luca Benini, who is now in University of Chicago. So I think we can start with the next slide. The non-linear ensembles I'm interested in actually come from the motivation of neural network. So I will give a few words on that. So in a neural network, we take an input column vector X with dimension n, and this goes through multiple layers of alternating linear and nonlinear function. Okay, so let us consider a single layer, for instance, and the important thing is that a nonlinear function f, which is the Relu function here, the max of 0 and x, is applied component-wise to a matrix times x. Okay, W run is a P times n matrix. And when there are multiple layers, this is simply a multi-stage architecture, both of alternating layers with both linear and non-linear such functionals. Okay, so this is a rather complicated object. And when one wants to modelize such a network, the aim is the following. So in principle, we would like to learn those matrices W2, W1, there's a synaptic weights. And for that, we can use different techniques. So we can use stochastic or not gradient descent. Also, in the modelization, there are multiple choices for the activation function. So I gave one example with a Relu function. So it is known that it accelerates learning, but it may also be problematic because the process can die. One can also use some other usual function, which are the sigmoid function or the hyperbolic tangent one. And one of the possible questions is what do we do when we learn these weight matrices? How do we learn, and what do we learn? And to understand how it works, we will now use the fact that the network widths may grow to infinity, or may be large enough so that random matrices can be of use in this theory. So for that, we take this time, instead of a vector, we simply consider simultaneously how many p vectors with dimension n. So this means that we consider a deterministic matrix of input data, and Y will be the target data set. Here I consider the case where there is a single layer. So as I said, we will add some randomness. So W will be m times n random matrix with ID entries. Okay. So the output of the neural network is simply, again, the non-linear matrix model, which is f of wx. And to estimate the output, we will use a linear interpolation. That is, we use a matrix B, and considers the matrix C, which is B star f of wx, and compare it with the target data matrix, okay? And this gives an error which is simply a linear combination of the error we make on each of the columns vector of y using z, okay? As it is quite usual in this interpolation procedure, we add regularization factor gamma, including the Frobenius norm of the matrix B. This is useful to avoid what is called overfitting in such learning procedure. And then we can compute, because this is linear interpolation, the optimal matrix B. And we get this formula on almost the last line. So what does it say? It says that the optimal matrix B is related to the resolvent of the matrix M star M, where M is a nonlinear random matrix. Okay, and what is especially important for the sequel is that the error we make just using this linear interpolation depends on the spectral measure of the matrix G, which is a sample covariance matrix, and which is M star M divided by P. So this is a usual sample covariance matrix, except that it is a nonlinear ensemble. Okay, so now I turn on the next slide, please. I turn to a brief review of some existing results about such nonlinear ensembles of random matrices. So this is first a result by Luar Liao Couillet 3 years ago, where they consider the case where W is sub-Gaussian, F is a Lipschitz function, and all the dimensions M and P grow to infinity in the same way. I recall that X is N times P and X is N times P, W is M times N. And they show the following results. So the empirical eigenvalue distribution of the matrix G has the same limit as another empirical eigenvalue distribution, which is defined through an equation for its Stieltjes transform. So below here is a series of equations. So the Stieltjes transform of this distribution mu bar satisfies a fixed point equation, okay, which is also on the last line. And there are just a few facts about this limiting distribution. So first, the dependence on the function f. So all this dependence is actually hidden in the matrix G bar here, which is the expected value of m stars m divided by p. So the first question which comes to mind when one considers this random matrix theory result is about maybe universality. So Luar, Liao, and Couillet show that this limiting distribution is not universal in the same way as the Wignerson circle distribution, because they can show that the first moment of the entries of W, indeed plays a role in the asymptotic distribution. Nevertheless, this is still some kind of universality result, because the role of moments of higher order is not important at all. Okay. And another comment about this complicated equation. It's actually a limiting distribution, which is quite well known in random matrix theory, because if one considers a matrix T such that TT star is equal to G bar, then mu bar is actually the limiting empirical eigenvalue distribution of Tx times its transconjugate if X has Gaussian entries with variance 1 over square root of P. Okay, so this is a result which actually states that the limiting empirical eigenvalue distribution of this first nonlinear ensemble is the same as that of a linear ensemble. And now I will turn to results completely in the same vein for nonlinear ensembles on the next slide. Okay, so the first result actually of this kind goes back to Noureddin El-Karoui, who studies some kernel random matrices. So more precisely, he considers a random matrix, which is a function f evaluated again component-wise at the scalar product between two column vectors xi, xj of a random matrix X. So X is here, and X is essentially sigma to the 1/2 times a standard P times N random matrix. By standard, I mean that the entries of Y have a finite force moment, okay? So the normalization chosen by El-Karoui is that we divide this scalar product by P. And then he considers the case where so the matrix sigma is deterministic. Okay, it is bounded and its normalized trace converges to some limit. Under some regularity assumption of F, which are not precise at all here, let me refer to Noureddin's paper for completeness. He can show that the matrix M can actually be approximated in the operator norm by a linear combination of three matrices: the identity matrix, the J matrix with all entries equal to 1, and the sample covariance matrix XX star, okay, with the good normalization. Okay, so in particular, the asymptotic empirical eigenvalue distributions of the two ensembles coincide. And then there was another result of Cheng-Singer 2 years later with some other assumptions on F. So they almost consider the same ensemble, except that normalization is square root of P instead of P. And also, we need, in this case, to set the diagonal entries equal to 0. Okay, and sigma is equal to the identity matrix in this case. So they show that the limiting empirical eigenvalue distribution is a deterministic limit, which is actually the free convolution of the semicircle distribution and the Marchenko-Pastur law. So again, this is a statement that from the random matrix point of view, we could say nonlinear ensembles are not so interesting because in the limit, we always get the same empirical eigenvalue distribution as that of a linear ensemble. Okay, but Fan and Montanari have shown that something can happen for these nonlinear ensembles, and in particular, the behavior of extreme eigenvalues may be completely different. They indeed show that due to nonlinearity, some eigenvalues exit the bulk of the spectrum. So there are indeed some interesting features in this model. Okay, we can turn to the next one. And actually, I will try to briefly give here some motivation why it's such ensembles are interesting regarding machine learning applications. So I'm cheating a little bit because it's not really a random matrix here, but on some forthcoming slide, there will be some true ones. So suppose one wants to learn a function f from independent samples, xi, yi. So here yi is a real number. And when I consider random vectors or random variables, here everything is Gaussian. So I will suppose for ease here that the neural network has only one layer, but the result I will state below by Jaco Gabriel Ongler has been proved in the multiple layer case. So yi is, there is an abuse of notation here, is the best estimate we can get of the function f using our neural network. So this means that yi will be obtained from the right-hand side using some optimization by gradient descent. So we simply use a scalar product of a Gaussian random vector with the output of a single layer of our neural network. And there is some noise, which is again modelized using some Gaussian noise. So the idea used by Jaco-Gabriel Ongler is to put as a parameter all what is not known, what is random in the neural network, and to consider the least squares, the L2 norm for the error. So when one performs a gradient descent using these parameters, the equation, the differential equation on theta is not nice. But, and this is the great idea, it gives a linear differential equation if one considers the difference y minus f theta of t of x. Okay, so f theta of t is simply this function f theta above evaluated when the parameter is upgraded according to the gradient descent. And what is important in the proof is that in the limit m goes to infinity, the kernel k, which is j star j, and j is simply the gradient of the function f theta, converges to some limiting kernel k0, which is called the Newell tangent kernel, and it remains approximately constant during training. So I'm cheating a little bit, but this kernel K0 is really like the kernel matrices we actually study in our nonlinear random matrix models. And I will come back on their results in a few slides. Okay, we can move to the next slide. Okay, so the model I will be interested in is a variation of that of Loire-Liao-Couillet. And it has first been introduced by Pennington and Vora. So they consider the case where everything is random. So what I mean is that the rate matrix is random. So it is assumed in the model to be a Gaussian random matrix with ID entries. But they also assume that the input data and the target data are Gaussian random variables with independent entries also. And we do the same as Loire-Liao-Couillet. So we consider the nonlinear ensemble f of wx divided by square root of n, and consider the matrix G, which is mm star divided by p. Sorry, G will be this matrix. And with the same minimization problem as that in Loire-Liao-Couillet. And we have the same result, which states that if we are interested in the error we make in using linear interpolation, then what is important is the limiting empirical eigenvalue distribution of this matrix G. And then Pennington and Vora have shown the following, using that all the matrices W and X are Gaussian. They show that there exists a limiting distribution mu f, provided all the dimensions grow in the same way to infinity. So m over n converges to some constant c, and m over p converges to some constant phi. And they give actually a quartic fixed point equation for the Stieltjes transform of this distribution mu f. So the way they prove it, thank you, is they simply use a saddle point argument using in the computation of the moments of the matrix, the threshold moments of the matrix G. And with Luca, we have tried to show that the result holds for much more general ensembles of random matrices. So a much wider class than Gaussian matrices. We assume that W and X have entries which are centered of variance 1 and have sub-exponential tails. We actually, because of the assumption on the entries of W and X, we have to make some rather sharp assumptions on the function f, which is real analytic, and there are some more conditions. And here for ease, I will assume that the function f is centered with respect to the Gaussian distribution. This is not needed because this is simply a rank-run modification of our matrix. And then we obtain the following, is that if we consider again the matrix G, its empirical eigenvalue distribution converges to the same probability distribution mu f and that of Pennington and Vora. Okay. So what can we say? Thank you. What can we say about this distribution mu f? This is the same as that of Pennington and Vora, and it is defined thanks to two parameters, theta1 of f, which is simply the average of f squared with respect to the Gaussian distribution, and theta2, which is the squared average of f prime, the derivative of f with respect to the same Gaussian distribution. And for completeness, I give here the quartic fixed point equation for the Stieltjes transform. Okay, so there are some questions about this quartic equation because in principle, just we have 4 possible solutions, but there are some conditions using the fact that it's the Stieltjes transform of probability measure. So actually, we can characterize the limiting distribution mu f using this equation. But let me turn to the next slide. Okay, and actually we can describe this limiting distribution mu f in another way. So it's actually the limiting empirical eigenvalue distribution of an information plus noise sample covariance matrix. So how do we construct this matrix? I will need 3 Gaussian matrices with ID entries. I don't insist on the dimensions, but they have the good dimensions, okay? So that at the end, we obtain M times M random matrix. So this is simply the same distribution that of the sample covariance matrix obtained from Gaussian matrix Z plus what we call a product Wishart matrix, which is the product of W and X. Okay, and simply you have to fit the parameters. So you have to choose square root of theta 1 minus theta 2 in front of z and so on to get the appropriate distribution in the limit. So this is again the statement that for this fourth ensemble of nonlinear random matrix ensemble, the limiting empirical eigenvalue distribution is the same as that of a quite well-known linear ensemble. And this is related also to a result of Florent-Beneiche, and in the same spirit as that of El-Garoui and Cheng-Singer. Okay. Can we change the slides, please? Okay, a few remarks about this result. So first, the dependence in F lies in the two parameters theta 1 and theta 2 only. And I recall that the just average of F with respect to the Gaussian distribution. So this means that this is a complete universality statement. So this may be of interest regarding machine learning applications, because sometimes people don't use the Gaussian distribution for the weight matrices, but say the uniform distribution can be used also. Another remark is about special cases for the limiting distribution μf. So if theta 2 is equal to 0, the distribution μf is simply the Marchenko-Pastur distribution. And if, on the contrary, theta 2 is equal to theta 1, so μf is this time the same as a limiting distribution as that of a product Wishart matrix. So actually one can show that if theta 2 is equal to theta 1, f is linear. So this is not really a surprise. So this limiting distribution has been studied. So there are some references missing here by Dupic-Castillo, Ekman, and it may also be known as the Rayleigh distribution. There has been a lot of papers about this distribution in the last decade. And in all other cases, as I explained in one of the previous slides, this is some kind of interpolation. Okay. So to finish with this slide, this may be also of use regarding machine learning applications, because one can easily compare the error we make by choosing one activation function or another. So this may help in comparing just in a very rapid way activation functions. Okay, we can change. Oh, so here are a few examples of the possible limiting distribution. The first one is an interpolation between Marchenko-Pastur distribution and the product Wishart case. And the second one is because the function that is even, so theta 2 is equal to 0. In this case, we get the Marchenko-Pastur distribution. Okay. So I will turn now to the multi-layer case. So far, this is, we have stated results about only one layer, but we can also consider a fixed number of layers. So simply considers a series of rate matrices with independent entries. So the dimensions may change from layer to layer, but we simply form the output of the neural network after each layer. So the output of the first layer enters the second layer, and we get the output after layer 2. So what is important here is that at each step, at each layer, we rescale the matrix entries of our output, say ml-1, by square root of the variance, so that at each step, the variance is scaled to 1, okay? And we simply form at each layer the matrix GL. So we were able to consider with Luca the case where theta 2 is equal to 0 with the same assumptions on F. And what we show is that provided the number of layers does not grow with n, the limiting distribution of GL is always the Marchenko-Pastur distribution, but the aspect ratio depends on the layer. But this is consistent. This always coincides with the aspect ratio of the final matrix we consider. And this has been extended in a recent paper by Fan and Wang, who considers a case where W is Gaussian, but where theta 2 is not 0. In all cases, we get a free convolution of the Marchenko-Pastur distribution and the limiting empirical eigenvalue of the matrix at the previous layer. Okay, so it seemed that the spectral measure obeys some kind of recursion formula. Okay. So regarding possible applications of this result, I first mentioned the same paper by Fan and Wang, who actually extend the result of Jaco-Gabriel Ongler to the case where the network width is comparable with the size of the sample, which means that n, which is the size of the sample, grows in a comparable way with p, which encodes one of the dimensions of the rate matrix. Okay, so they consider actually let me say, a matrix which can be random or deterministic for the input data, but it keeps some of the features of a matrix with ID entries. So the important features is that the columns of X are approximately orthonormalized. Okay, and the important factor is the orthogonality assumption, actually. And what's more, it's empirical eigenvalue distribution for X star converges to some probability mu0, and there are L layers, okay? And I need to mention one more thing, that we will perform gradient descent. There will be really learning, but only after layer N. Okay, we don't learn the first layers, but just the last one. And what they show is really the analog of Jaco-Gabriel Ongler's result, but regarding the spectral properties of the matrix. So as n goes to infinity, the Gram matrix of the Jacobian, which comes from the gradient descent, converges to some limiting kernel K0. So they cannot describe it. But what is important is that the spectrum of this limiting kernel is the same as that of a linear combination of the identity matrix and the sample covariance matrix we obtain from the output after each layer. Okay? And the limiting empirical eigenvalue is characterized. This is the limiting distribution I gave on the previous slide, actually. So, so far, this is all we can do about this particular regime, right? So, the sample size is linear with respect to the network width. We can describe the kernel, the limiting kernel, just from the spectral point of view, but this is quite interesting. So I will just skip the two next slides because I won't have the time to explain it. That's this one. Yeah, thank you. So I will turn to some ideas for the proof of the universality result. So I will come back to the idea of Pennington-Vora, and we use a simple moment method. So basically, we start with a polynomial function f. And to explain the ideas, I will consider an odd monomial to start and explain briefly how it works in general. So I choose this function, which is a monomial, and then I want to compute the expected value of the trace of G to some power Q. Okay, so we just develop this trace, this moment, and develop everything in terms of all the random matrices. So this gives a rather big formula, but the first product here is simply Wx I1 J1. Okay, except that we have developed in terms of some L indices. So for ease, I will assume first that all the I and J indices are pairwise distinct. And we will encode this on the next slide by using some black graph, which is simply the graph on I and J indices. Okay, because I'm computing a trace. This graph is a cycle. I assume that all the I and J indices are pairwise distinct. So this is a cycle with two Q edges. Okay. And now to encode the W and X entries, I have to use my summation on the L indices. So each we call an edge I1, J1 a niche, and each niche will be decorated by L blue points. So they stand here for each such entry WI1L XL J1. Each blue point has a meaning. So, okay, we come back to Wigner's proof. And we use the fact that all the entries are independent and centered. So we have to match the blue points in such a way that each of the W entry and X entries has to arise at least twice. Okay, and let me go to the next slide. Because now we have chosen an odd monomial, the typical way, that is the way that maximizes the number of pairwise distinct indices, is the following. in each niche, we choose an L index, which is going to be matched with one index from each niche. This gives a long blue cycle here. And otherwise, the remaining blue indices inside niches are matched using a perfect matching. Okay, so this is true actually only if Q is greater than 1. If Q was equal to 1, one would simply perform perfect matching on the corresponding 2K edges. This is a special case because a long cycle of length 2 is actually just a matching. Okay. And then on the next slide, this will give actually the two parameters theta 1 and theta 2. Because for an odd monomial, if k is equal to 2p plus 1, we simply have to choose the index which is in the long blue cycle. There are 2p plus 1 such choices. And then we get the number of perfect matchings in of the remaining indices. And this is actually theta 1 of the monomial xk. This is theta 2. Sorry, I always mix the two parameters. And if q is equal to 1, we just have 4p plus 2 double factorial matchings. And this is theta 1. Okay? So this is where the two parameters come from for an odd monomial in a long cycle. And then on the next slide, we can show the following. So typically, the black cycles are not only a long cycle with 2Q edges, but they are what we call cactus graphs. So this means that a typical black graph is a tree of cycle, which means that an edge, if you choose an edge, it belongs to exactly one cycle. Okay, so for instance, the identification, which is in a red dotted line here, is not possible. Otherwise, the graph does not contribute to the expected moment. And once you have formed these black graphs, then one does the same thing regarding the blue matchings. This is always the same. So for instance, a small black cycle of length 2 will give a contribution which is theta 1. Instead, a long cycle of length, 46 will give a contribution which is theta 2 to some power which is probably 46. Okay, and in the limit, on the next slide, please, we obtain that the moment is simply the sum over all the cactus graph. So A of Q here counts the number of cactus graph, and each small cycle of length 2 is rated by a factor theta 1 and others by a factor theta 2. Plus there are some terms which depend on the dimension. And if theta 2 is equal to 0, let me just mention that one gets the contribution in the limit only of those graphs with small cycles of length 2. I'm speaking about the black graph, and in this case, one recovers the number of fat trees. Okay, and if theta 1 is equal to theta 2, this is simply a sum not weighted by the same weight actually on all the cactus graph, disregarding the difference between long and cycles of length 2. Okay, I'm pretty late, so in a word, if the monomial is even, so there is simply this fact that we have centered the function f with respect to the Gaussian distribution. So this amounts to band perfect matchings inside each niche. And we prove at the end that everything is negligible except the contribution from graphs with cycles of length 2 only. And then we extend the result to an arbitrary polynomial and then to our class of activation function by Taylor approximation. So we can go to the last slide. Which is just about the conclusion for the talk. So can you skip 2 more slides? Okay. So what I haven't said is that I consider real random matrices. In the complex case, the limiting distribution has 2 possible distribution, which is either the Marchenko-Pastur distribution or the product-Wishart distribution. Okay, but there is no interpolation limit between these 2 ones, provided this condition is satisfied. So what is left here is the behavior of extreme eigenvalues. So if we perform some simulations, there may be some outliers, in particular in the case where the function f is even, and this has some impact on machine learning, on the training, and on when one has to stop training, because it is known that training is faster when one considers the direction of the eigenvectors associated to the largest eigenvalue. And last, because it urges, it would be interesting probably to consider heavy-tailed random matrices instead of X with sub-Gaussian tails, or for the rate matrix, sorry, most importantly, because our choice makes all the entries of X quite uniform, and maybe for machine learning application, it would be interesting not to do so. Okay, sorry for being a little bit long, but I thank you for your attention.
Well, all right, I'm back in. So, are there any questions?
So why is this not working for max function?
Oh, because of our terrible assumptions on f, which has to be real analytic. So in principle, we could approximate the max function and derive the result, but this would require some more work. And yeah. This is not completely impossible. We believe something could be done, but we did not really try.
So how do you identify the correct solution of the quartic?
Oh, this comes from the moment computations, actually, because you can start from the Marchenko-Pastur distribution when you only have the cycles of length 2. Okay, so 3 of cycles of length 2. And in comparison for the nonlinear ensemble, you add this long graph all are weighted by theta 1 to some power, but they all have the same weight. Okay, and when I think you consider the linear ensemble, it comes to cite that they are indeed the same moments.
Okay. So, are there any other questions?
I have a short question about this last extension that was mentioned to heavy-tailed random matrices. If you're using the method of moments, you might run into troubles, or especially if there is some dependence. Would you try to use a different approach, or do you think this is possible with method of moments still?
I'm almost sure that we will get into troubles, but there is some hope that something can be done, maybe, and because probably influenced by the fact we are looking at the largest eigenvalues. So this may be easier in this case. I don't know. I think, we don't have the approach of Pennington-Vora for heavy-tailed random matrices. We can only hope that something could be done using moments or using the resolvent approach, because I did not mention that Fan and Wang use a resolvent approach to derive a similar result. But one of the matrix is Gaussian. So we will get into trouble, but we hope something can be done.
And if I may ask one more question, I was also wondering if it is possible to incorporate these sample correlation matrices into your random matrix model somehow, because there is some nonlinearity there compared to sample covariances, and for sample covariances you know everything, and this looks very similar. And also this alpha heavy Marchenko-Pastur law, if I had to guess, I would say it's some free convolution between Marchenko-Pastur and something else, and this is the same phenomena that you see.
Oh, maybe. And that's a good question. I don't have a feeling about that directly, but why not? Probably it's true. Didn't think about correlation matrices, but that's an interesting question.
All right. Are there any other questions?
Is there something known if there are a variable number of layers? Or you need something fixed?
Okay. And a number of layers which grows to infinity?
Yes.
I don't know any such results, but I've not read the huge literature about all existing results. No, I don't know.
And for the microscopic scale of the eigenvalues, is there something expected, or is it also
I don't know.
Ensembles? Or?
What I think the comparison with linear ensemble goes, at least from Fan and Montanari's result, it still holds true regarding the largest eigenvalues. So what I mean is that the localization of the largest eigenvalues is the same as that of a more precise linear ensemble. Okay, one needs to add a finite rank matrix to just Wigner plus Marchenko-Pastur. But we don't know so far about the size of the fluctuations. We believe, at least for the edge, this would be in the scale 1 over square root of n, where there are some outliers. But even with simulations, it's difficult to see because the convergence is not so rapid as it is for linear ensembles. So I can't give a precise answer.
Okay, but there are some outliers like this finite rank of operations.
Yeah.
All right. Anyone else? So I'd like to thank Sandrine for a wonderful talk, and I'd like to thank all the speakers and all the people who attended for being here and for having a wonderful conference. Now, in the good old days, I'd be taking the speakers out to dinner, but I'm afraid that given the circumstances, we shall all have to go to our own dinner. So, thank you very much.
Thank you.
Thank you.